Hello, my name is Nigel Peare. I'm going to talk to you today about computational thinking. Computing is all about solving problems. And we have several tools in our toolbox to solve those problems. Imagine yourself going on a journey from here to Cardiff. You might like to break down your journey into several smaller steps. We call this decomposition, breaking down your problem into smaller problems so that they're easier solvable. One of the other tools we have in our toolbox is abstraction. Abstraction is where we take away all the excess detail that we don't need to solve our problem. Pattern recognition is another tool in our toolbox. We may have seen our problem before. We may have gone to Cardiff before. So we may already know the pattern that the route will take. Algorithms are recipes that give us instruction as to how to solve a particular problem so that we can solve that problem step by step. Here's a little puzzle for you. You're a tour guide. Tourists staying in your hotel expect to be taken on a tour visiting the city's attractions. You've been given an underground map that shows all the locations of the attractions and how you can get from one to another using the underground network. You must work out a route that starts from the hotel and takes your tour group to every tourist site. The tourists will be unhappy if they have to pass through the same place twice. They also want to end up back at their hotel that evening. So what I'd like you to do now is to take a look for a route that with those criteria that will lead you around this map. But I also want you to think about the patterns you might see when you are doing that and why those patterns exist when you are going around your map. Stop the video now and see if you can work out a route. Okay, so now maybe you've come up with a route. It might be from the hotel to the Science Museum, from the Science Museum to the toy shop, from the toy shop to the big wheel, from the big wheel to the park, onto the zoo, next the aquarium, then the art gallery, the waxworks, warship, the castle, cathedral, and finally back to the hotel. You may have thought about the patterns that are occurring here as well. So you might like to go around the outside cycle first, as I've done here, and then go into the inside cycle and go around that. Or you may have gone into the inside cycle first and gone around the outside cycle. There are several routes here that follow those criteria, but basically that same pattern exists. Now, let's move on to something else. Here's another little puzzle for you. A single chess knight is able to move on the small cross-shaped board below. You'll know that if you play chess, that a knight can move 2 spaces in one direction and then move 1 square at right angles or vice versa, as shown. It jumps to the new square without visiting any in between and must always land on the square on the board. So what you need to do is to find a sequence of moves that starts from square 1, visits every square exactly once by making such knight's moves, and finishes where it started. So we can see that If the night is starting at 1, he can move to 6 or to 9 or to 7. And from 6, he might move to 8. From 8, he might move to 2, etc., etc. What I also want you to think about when you are looking at this puzzle is to look for patterns that occur within the routes you can find. There are actually several routes through this puzzle. But also, I want you to think about a solution, a help to the solution to this problem. And I want you to think back about our city problem, for example, which might help you. Stop the video now and see if you can find a route or even two. So maybe you've come up with a solution and found a route around the knight's move puzzle. One of the ways that we can look at this puzzle is exactly the same way as we looked at for our hotel guide problem. So if we think about the square we are starting at, number 1, from number 1, we can make our way to number 7. We can make our way to number 9. We can make our way to number 6. From 6, we can go to 12. 6, we can go to 8. From 7, we can go to 5. From 12, we can go to 7. From 12, we can go to 4. From 5, we can go to 11. From 9, we can go to 3. From 8, we can go to 2. From 4, we can go to 10. From 3, we can go to 11. From 2, we can go to 10. From 10, we can go to 11. And from 2, we can go to 3. Now we can see, by abstracting the data that we have and how we can move between the squares into our map, we can actually map our way through the puzzle. So if we wanted a route, we might go 1, 9, 3, 2, 8, 6, 12, 4, 10, 11, 5, 7, 1. Or we might go 1, 9, 3, 11, 5, 7, 12, 4, 10, 2, 8, 6, 1. There are several routes through this, as you can see. But by abstracting the data that we've got into our problem map, and by decomposing the problem into those several short steps, you can see how easy the problem has now become. Okay, that's my talk for today. We've talked about decomposition, abstraction, pattern recognition, I hope you've enjoyed it.